A particle is projected from the origin with initial velocity u to pass through a point AB. Prove that there are two possible trajectories if this condition holds, and assume that there is no air resistance. Alright, so this question is going to be a bit of a tedious and long question. Let's get started. Now, I have a particle being projected from the origin. This is what it looks like. It's going to be projected like this as a parabola. Let's extend that. So this is my x direction, this is my y direction. I have an initial velocity, which is like this, initial velocity of u, and well, let's call this bit here alpha, or theta, or anything really, just an angle here. So it has a magnitude and an angle. Okay, now, this is a projectile motion question, and I'm not given the equations for x or y, or the velocity in the x direction, or the velocity in the y direction. So I really have to derive them from first principles myself. And it's a good exercise as well. It's good to see this. It's good to be able to reproduce it in an exam if the situation comes up where you need to do so. So, we're assuming there's no air resistance. Now, projectile motion, we break it down into horizontal and into vertical components. Let's consider the horizontal component first. The horizontal component, there is no force acting on the particle in the horizontal direction, because we are assuming that there's no air resistance. So if there's no force, there's no acceleration. So x double dot, which is the notation that we use, hopefully you're familiar with that, x double dot is equal to 0. Great. Now x dot is going to be the integral of x double dot, which is 0, with respect to time. Now the integral of 0 with respect to time is just going to be a constant. So this is equal to a constant, and let me call that constant C1. Now I need to work out what C1 is. So when t is equal to 0, my particle is here at the origin, and it's at the origin because I've defined my axis as such. I've defined that I start at the origin, which is usually the most convenient thing to define. So t is equal to 0, but what is the x component of the velocity? Now if I take the velocity vector out, the initial velocity vector rather, that's equal to u, and there's some sort of angle that it makes here of alpha. Now if I resolve this into two vectors, here is my uy, and here is my ux, or maybe I'll put it here so you can see it, ux. And yes, I haven't joined these, but that's just an error on my account in drawing. So ux is going to be, if I just used Pythagoras' theorem, I would get what? I would get ux equal to u times cos alpha. So u is equal to, or ux, or let's actually call it x dot, since that's what we're using here, is equal to u cos alpha. And so therefore, if I sub these in, that's just going to mean C1 equals u cos alpha, which means that x dot is u cos alpha. Fine. Integrating to get x. U cos alpha is really just a constant with respect to time. It's no time variable, so integrating it is u times t cos alpha plus another constant. Let me call that C2. I need to work out C2. When t is equal to 0, x equals 0. So I sub them in. 0 equals 0 plus C2. So C2 is clearly 0, so therefore x equals ut cos alpha. Great. That's in the horizontal direction. Let's consider the vertical direction now. In the vertical direction, well, there's only one force acting on the particle in the vertical direction. At any point here, I have an acceleration of gravity pulling the object back down to Earth. So my acceleration is equal to g but not just g, it's minus g, because my positive direction of motion, according to my axis here, is up, and the acceleration is down. So once again, I fall into that trap. It should be y double dot, not a. Y double dot equals negative g. To get y dot, I integrate negative g with respect to t, and I will get negative gt plus a constant. Let's call it c3. I need to work out what c3 is. So when t is equal to 0, what's y dot equal to? Y dot, or as I wrote here, uy, but I really should have written y dot, is going to be, well, that's going to be u sine alpha. Again, that's just using sine equals the opposite over hypotenuse and then rearranging. So that's not really too much of an issue, hopefully. U sine alpha. And so if I sub that in, that would tell me that C3 is going to be 0 equals negative 0, which is really just 0. Or that should be, let me write that again. So that's u sine alpha equals 0 plus C3. So C3 is u sine alpha. Putting that back in here, I get y dot is equal to negative gt plus u sine alpha. Great, now I want to get y, so I'm going to integrate this with respect to t, and I'll get negative g t squared on 2 plus, this is now a constant in terms of t, well, constant with respect to t rather, so ut sine alpha when I integrate it, plus another constant, my fourth constant, c4. Now when t is 0, y is 0, because that's how I've defined it. So 0 equals 0 plus c4. c4 is equal to 0. And so therefore, y is equal to minus g t squared on 2 plus ut sine alpha. And hopefully these would look familiar to you in terms of, usually you're given these in a question, but in this question we're not given it, so technically we need to derive them from first principles. So that was just deriving them, and let's see where we go from there. Now, the question says that the particle passes through this point a comma b. So a is clearly the x coordinate, b the y coordinate. That's obvious to us. But we don't have x related to y in an equation, so we need to go ahead and do that. And by doing that, what we're actually doing is we're finding the Cartesian equation which describes the path or the trajectory of this projectile. So I'm going to use what I've just derived. X is equal to ut cos alpha. Now I'm going to rewrite this and write it as t equal to x on u cos alpha. And I'm going to call this equation 1. And what else had I worked out? I'd worked out that y equals negative gt squared on 2 plus ut sine alpha. And I'm going to call this equation 2. Now you can see that my individual components x and t were both in terms of t. So this is kind of like a parametrics sort of question where I have x and y defined in terms of one variable. So I really have one variable that describes the motion. Sort of like that, but not really, but we can think of it in that manner. And so I can eliminate this variable t to get y in terms of x. And so let me do that. Let me substitute 1 into 2. And what do I get? I get y equals negative g on 2. Now t squared, well t is x on u cos alpha. And if I square that, that's what I get. Plus u, now t is x on u cos alpha times sine alpha. Alright, so I have minus g x squared over 2 u squared cos squared alpha. Here I have a cancellation with the u's, and I'm left with x times sine on cos. Well, sine on cos, we know that as tan alpha. Great. And that's what y is equal to. Alright, so now we can substitute our point AB into this equation because we have y in terms of x. So substituting a comma b in, and the reason that we substitute it in is because we're told that it passes through this point. That's the question. we're told that it passes through the point AB. So if it passes through the point AB, AB must satisfy the Cartesian equation, or the equation which describes the trajectory or the path of the projectile. So substituting that in, I have B equal to minus G A squared on 2U squared cos squared alpha plus X is A tan alpha. Alright, let me multiply, or not multiply, bring this cos squared alpha up here. And by doing that, it becomes a sec squared, because 1 on cos squared is sec squared, alpha tan alpha. And now we're going to use one of our trig identities, recalling that sec squared alpha equals 1 plus tan squared alpha. And you'll see why we do this in just a second. B equals minus G A squared on 2U squared 1 plus tan squared alpha plus A times tan alpha. I want to get rid of this 2U squared in the denominator, so multiply the whole equation by 2U squared, and I should be consistent and keep my U's as capitals. So 2U squared B equals negative GA squared, and I'm going to expand by distributing this through here. I'm going to expand out, minus GA squared tan squared alpha plus 2U squared times this, so 2U squared A tan alpha. Okay, now let me rearrange a little bit, bring everything onto one side. So if I bring everything over to this side, I'm going to get GA squared tan squared alpha, bringing this over, minus 2U squared A tan alpha, and bringing this over here, I'll get plus 2U squared B plus GA squared equal to 0. Great. Now let me go back to the question for just a moment. The question said, to prove that there are two possible trajectories if this condition holds. Now, how could there be two possible trajectories? Well, that's dependent on what this value of alpha is. If the alpha was like larger, it would go like this. And if it was smaller, it would go like this. Now, we're being told that there are two possible trajectories, so we need to find a way to say that there are two possible values of alpha. And hopefully you can see this equation here as really a quadratic equation in terms of tan squared alpha. And we know that a quadratic equation has two solutions. So this is a quadratic equation in terms of tan alpha. Now, I said that this has two solutions, but it only has two distinct solutions, two real distinct solutions under a certain condition, and that is that the discriminant is greater than 0. Remember, if it's greater than 0, I have two distinct and real solutions. If it's equal to 0, I have one repeated real solution. And if it's less than 0, I have two complex solutions, which are distinct unless these are complex numbers, then could possibly be a repeated root. But anyway, we want obviously to have real values for our angle. We're not going to have complex values for an angle, so we have two solutions, two real distinct solutions if the discriminant is greater than 0. Alright, so what's the discriminant here? The discriminant is b squared, which is minus 2 u squared a squared, minus 4 times a, which is ga squared, times c, which is this constant term here, Okay, now let's expand and simplify. V u to the 4a squared minus 4. Now I'm going to leave a factor of 4a squared out here and just distribute the g through. And the reason is because I see that I'm going to be able to cancel a 4a squared here. So distributing just the g through here, I get 2 bg u squared plus g squared a squared greater than 0. And then I'll be able to cancel the 4a squared here with the 4a squared here. And so I'm left with u to the 4 minus, what do I have? 2bg u squared minus g a squared. Is it g a squared or is it g squared a squared? It's g squared a squared greater than 0. So let's have a look at what our question wants us to have. We're almost there. We have u squared minus gb all squared is greater than g squared into a squared plus b squared. So I want to get this u squared minus gb all squared into it. And I can see that here I kind of have a quadratic in terms of u squared. If I can complete the square to get what I want, then I think that's the way to go. So I have u to the 4 minus 2bg u squared. Now by completing the square, I'm going to halve this and then square it and add it on. So halving 2bg is bg, squaring it is going to be b squared g squared. Put that in brackets. But I've added b squared g squared, so I have to take it away because I can't do anything for free. G squared a squared is greater than 0. Cool. Now here I can recognize this as a perfect square. It's going to be u squared minus bg all squared. Now if I move these over here, I get b squared g squared plus g squared a squared. And just to be consistent with the question, we're pretty much done now. Just to be consistent, I'm going to write it as gb squared is greater than g squared into a squared plus b squared. And here we have that condition that we were asked to prove. So if we have this condition, that means that our quadratic equation in terms of tan alpha has two real distinct solutions. And if it has two real distinct solutions, that means there's two values of alpha. If there are two values of alpha, then our projectile has two possible trajectories. And that is the end of the question.